Hello again, analysis students. So, this is part 2 of the lecture on Cauchy sequences. Thus far, we've used the Cauchy criterion to prove that a sequence converges, which otherwise would have been difficult to show convergence of. But we didn't actually prove that a sequence is convergent if and only if it's Cauchy. So, this is on a page which is fair enough above. I'm going to write the statement of the theorem off to the side, along with a sketch of what it is that we need to show. So, what was, this button. Theorem 2.8.2 above the Cauchy convergence theorem. It says that a sequence is Cauchy if and only if it converges. And that theorem is totally meaningless if we don't point out what it means for a sequence to be Cauchy, which I'll remind you of right now. A sequence, A sub n, is Cauchy means for all epsilon bigger than 0, there exists a choice of big N such that for all little n bigger than big N, and for all little m bigger than big N, absolute value of a sub n minus a sub m is less than epsilon. So let's do it. So presumably it'll be very easy to show if a sequence is convergent, then a sequence is Cauchy. And in fact, maybe I'll sketch a picture of the proof of the forward direction right here. A picture of convergence implies Cauchy. So, by picture, I mean literally I'm going to draw a triangle. So, there's a sub n, there's a sub m. I would like the distance between them to be less than epsilon. Right? If I'm trying to show that a thing is Cauchy, then there's the conclusion that I need. I know that the sequence has a limit. Sorry, there was a jump right there. I noticed that this app did something very strange right here. I'm going to see if this fixes it. So I know that the sequence has a limit. I'm going to give that limit a name. Let's call that limit A. There's A. Now I know that if I let little n be big enough, then I can get this distance to be as small as I want. Where that little n, the big N comes from the fact that a sub n converges. Similarly, if little m is bigger than that same threshold number big N, then this side is less than epsilon. That'll give this distance being less than 2 epsilon, which isn't what I need. But at this point, we know what we need to do. If instead those things were less than epsilon over 2, this length would be less than epsilon, which would give me what I need. Cool. So let's now compose the proof. All right, so let's do it. Let's let a sub n be a convergent sequence. Let's suppose that the limit of this convergent sequence is a. It has a limit, so we may as well give it a name. I need to show that for every epsilon, there is some big N such that if little m is bigger than big N and little n is bigger than big N, then that difference is less than epsilon. So let's use the picture that was just drawn to figure this out. So this statement right here says how to come up with a choice of big N. So let's get our choice of big N. Let's write it down. Consider any epsilon bigger than 0. Since a sub n converges to a, there is some big N such that if little n is bigger than big N, then the difference between a sub n and a is less than epsilon over 2. The statement of Cauchiness now says that I should assume that little m and little n are both bigger than big N. Do that. Well then, since little m is bigger than big N, then a sub m minus a is less than epsilon over 2. And because little n is bigger than big N, a sub n minus a is less than epsilon over 2. Nice. So this statement right here says a is close to a sub m. It says here that a is close to a sub n. So let's just use that. That says that you should add and subtract a and use the triangle inequality, because that means this will be small and this will be small. So when you add them together, you'll still get something that is small. And now let's just show that they're small. By the triangle inequality, this is less than or equal to the absolute value, of a sub n minus a plus the absolute value of a minus a sub m. This is less than epsilon over 2 plus epsilon over 2. Hey, that's just epsilon. So let's see what we did. We started by considering any epsilon bigger than 0. We came up with a choice of big N. We assumed that little m and little n were bigger than big N. And then we showed a sub n minus a is less than epsilon. So, putting that together, this means that the sequence is Cauchy. Nice. Okay, cool. So we've completed half of the proof. We've proven that if a sequence is convergent, then it is Cauchy. Let's prove the other. So let's suppose, conversely, that a sub n is a Cauchy sequence. I need to show that a sub n converges. That is, I need to show that a sub n has a limit. Here's how I'll do it. Well, first I'll need to come up with a candidate to be the limit of a sub n. So let's do this off to the side. So how will we do that? Well, we have one good way of at least constructing a subsequential limit, and that is if we knew that the sucker were bounded. And every convergent sequence is bounded, and boundedness is such a weak thing that maybe we can start by showing that the sequence is bounded. Because if we can do that, then we can apply the Bolzano-Weierstrass theorem to get a subsequential limit. Notice I won't know what that subsequential limit is, but I'll know that it exists. If I know that it exists, I can call it a name. That subsequential limit will be a. Now, if a converges, and if a sub n converges, and this is a subsequential limit, then it has to be the limit. A convergent sequence only has one subsequential limit, so if this is a subsequential limit, then it's the only one. So the last step is to show that a sub n converges to that number a. Well, I guess let's get started. Step 1, show a sub n is bounded. Claim 2.8.4, a sub n is bounded. So this will feel a lot like the proof that every convergent sequence is bounded. Let's go ahead and do it then. So just like in the proof that every convergent sequence is bounded, I'll use a sloppy choice of epsilon. Let's take epsilon equal to 1, because that's a positive number, and because the sequence is Cauchy. So Cauchiness tells me something happens for every choice of epsilon. Here is a choice of epsilon that's bigger than 0. So that means that I can apply that for this epsilon. There exists some big N such that little m and little n are bigger than big N. Then absolute value of a sub n minus a sub m is less than epsilon. And maybe I'll even go ahead right here. If I solve for a sub n, what do we get? Well, you already know what we get, right? We've done this enough times. I'll get that a sub m minus epsilon is less than a sub n. Oh, and that epsilon is, of course, 1. Cool, so that gives me control over what a sub n can be. Unfortunately, that control depends on our choice of a sub m, and that's not the way a bound should look. Upper and lower bounds need to be like constants. So I'll make it a little bit more constant. Instead of, I don't need to know that this is true for every choice of little m. Here is a particular choice of little m, which is something bigger than big N. So I can use that as the choice for big M above, and conclude that for all little n bigger than big N, a sub big N plus 1 minus 1, that's in the subscript. This is in the subscript. This is not in the subscript. Is less than a, is less than a sub big N plus 1 plus 1. So what does this mean? This sure looks like these are bounds, but it doesn't quite actually give us that. It only gives us these bounds when little n is bigger than big N, which isn't what it means to be bounded. To be bounded, you need to have some bounds that apply for every choice of n, but how many natural numbers are less than big N? Well, finitely many. Finite sets are bounded. So let's just wrap this up. This will seem pretty familiar, I hope. Now, the set a1, a2, dot, 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 a sub big N, where this stops at big N is a particular number, is finite. Finite sets are bounded, and so is bounded. Let's let L and U be lower and upper bounds respectively for the sequence. Not for the sequence, for the set. All right, so now I won't finish the proof that the sequence is bounded, but I'll tell you what the upper bounds are. Then the max between the upper bound that walks when little n is less than big N and the upper bound that walks when little n is bigger than big N is an upper bound on a sub n, while the min between the two partial lower bounds is a lower bound. As a sub n is bounded above and bounded below, the sequence a sub n is bounded. And that completes the proof. All right, so we've just proved that a sub n is a bounded sequence. What does Bolzano-Weierstrass have to say? Well, Bolzano-Weierstrass says that because a sub n is bounded by Bolzano-Weierstrass theorem, a sub n has a subsequential limit. Maybe you would rather this say that it has a convergent subsequence, but that's the same as having a subsequential limit. Cool, so let's let A be that subsequential limit. Let's let A sub n sub k be a subsequence which converges to A. We know that one exists because it's a subsequential limit. And as per the sketch of proof before, there's only one thing that A sub n might converge to, and that thing is A. So we'll be done with the proof if we can just show that A sub n converges to A. There is the goal. And so let's try to do it. So I know how to complete a proof of a theorem of this form. All right, what do we need to do? We need to start by considering any epsilon bigger than 0. No, let's be over here. I need to start by considering any epsilon bigger than 0. I need to come up with a choice of big N. Make that a big N, not a big N1. I'll consider any little n bigger than big N, and then I need to show that the absolute value of a sub n minus a is less than epsilon. But I don't know immediately that a sub n minus a is less than epsilon in absolute value. So if there's this a, there's a sub n. Well, I can definitely, well, this is, no. What I want is I want this distance to be less than epsilon. And well, what do I already know that's close to A? Well, I know that A sub n sub k converges to A, the subsequence. So if there's A sub n sub k, then I can get this to be less than epsilon, provided that this parameter, little k, is bigger than some threshold value, big K. Let's see, this is a term in the sequence, that's a term in the sequence. As long as those are both terms that are far enough along in the sequence, they're close to each other by the Cauchy criterion. So I can get this length to be less than epsilon, as long as little n is bigger than some big N that comes from the Cauchy criterion, and as long as n sub k is bigger than big N, where this big N comes from the Cauchy criterion. Oh, nice. So this actually tells me everything. That tells me this epsilon needs to be divided by 2. That tells me this epsilon needs to be divided by 2, because then this will be an epsilon. So there's the idea of the proof. Now it's just a matter of doing it. So it looks like, what do I need? I need to use the fact that this sucker's Cauchy. I need to use this subsequence a sub n sub k, the fact that it converges. So let's just use those two things. Consider any epsilon bigger than 0. This is an epsilon n proof. Since a sub n is Cauchy, there exists some big N. I've just come up with my choice of big N, such that for a little n bigger than big N, the absolute value of a sub n minus a sub m is less than epsilon over 2. Cool. Since a sub n sub k converges to A, there exists some k such that whenever little k is bigger than big K, a sub n sub k minus A is less than epsilon over 2. All right. Now, I claim there is a choice of little k such that simultaneously little k is bigger than big K and n sub k is bigger than big N. Maybe I can even write down such a k. I think that little k greater than the max between k, because I need little k to be bigger than big K, and n, because if little k is bigger than big N, then n sub k will be bigger than or equal to n sub k. N sub k will be bigger than or equal to k will be bigger than n. So I'll get both of these happening simultaneously. For this particular choice of k, and any choice of little n bigger than big N, I get the absolute value of a sub n minus a sub n sub k is less than epsilon over 2. This is because the sucker's Cauchy. A sub n sub k minus a is less than epsilon over 2 because a sub n converges to a. by the triangle inequality, then the absolute value of a sub n minus a is equal to the absolute value of a sub n minus a sub n sub k plus a sub n sub k minus a. That's less than or equal to absolute value of a sub n minus a sub n sub k plus absolute value a sub n sub k minus a is less than epsilon over 2 plus epsilon over 2 is epsilon. So let's just read back through this. So I've zoomed out a little bit, and I'm going to use this to point. So I started by considering any epsilon. Oh, maybe I'll actually highlight. I considered any epsilon bigger than 0. I came up with a choice of big N. I considered any little n bigger than big N. On the way, there was also this little k that came up that was part of the proof, but not part of the conclusion. For that particular choice of n, I showed that the absolute value of a sub n minus a is less than epsilon. So that does it, right? Thus, for all epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, absolute value of a sub n minus a is less than epsilon. That means that a sub n converges to a as we claimed. Thus, given any Cauchy sequence, we have found its limit. That's what that previous claim was. So every Cauchy sequence converges. That completes the proof of the Cauchy convergence theorem. Then a little Halmos box to indicate that the proof is done. Great. Well, wonderful.